Good afternoon. I hope everybody can hear me. എൻ്റെ വീഡിയോയും കാണുന്നുണ്ട് എന്ന് വിചാരിക്കുന്നു. The presentation is showing design of FIR filters using frequency sampling in brown color. ആർക്കെങ്കിലും കേൾക്കാനോ അല്ലെങ്കിൽ വീഡിയോ കാണാനോ ബുദ്ധിമുട്ടുണ്ടെങ്കിൽ please let me know. Okay. So in the last class, we looked at the way of designing FIR filters using windows. മൂന്ന് വിൻഡോസ് നമ്മൾ പറഞ്ഞു. റെക്ടാങ്കുലർ വിൻഡോ, ഹാമിംഗ് വിൻഡോ, ഹാനിങ് വിൻഡോ. അതിൽ റെക്ടാങ്കുലർ ഹാമിംഗ് വിൻഡോ we had also seen an example. Okay. The next way of designing an FIR filter is using something called as frequency sampling. Frequency sampling you might have already heard. നമ്മൾ DFT പറഞ്ഞപ്പോൾ we told that DFT is actually the sampled version of frequency Fourier transform. കണ്ടിന്യൂസ് ആയിട്ടുള്ള ഫ്രീക്വൻസി ഡൊമൈനിൽ കണ്ടിന്യൂസ് ആയിട്ടുള്ള സിഗ്നൽ ഫ്രീക്വൻസി റെസ്പോൺസിന് സാമ്പിൾ ചെയ്ത് കിട്ടുന്നതാണ് DFT. ആ സെയിം കൺസെപ്റ്റ് തന്നെയാണ് FIR filter design using frequency sampling we are going to use. So what the design is about is like you have an ideal response for frequency. ഒരു ഫിൽട്ടർ ഡിസൈൻ ചെയ്യാൻ വേണ്ടിയിട്ട് ആ ഫിൽറ്ററിൻ്റെ ഒരു ഐഡിയൽ റെസ്പോൺസ് നിങ്ങൾക്ക് തരും. Ideal response means this is the response that I need to implement. So what we do is our response in it, our frequency response in it, that will be continuous. Our frequency response in it, we will sample. So when you sample in frequency, it is basically DFT. Okay, and what we want to find is the corresponding impulse response of the frequency response. അതായത് നമുക്ക് ഫൈനലി കാണേണ്ടത് h of n ആണ്, or the coefficients of impulse response. So frequency domain ഉള്ള sample ചെയ്ത് if you take the IDFT of the sampled values, you will get back the impulse response. h of n, h of 0, h of 1 അങ്ങനെ h of m minus 1 വരെയുള്ള സാമ്പിൾസിൻ്റെ റെസ്പോൺസ് ആണ്, or h of m minus 1 വരെയുള്ള സാമ്പിൾസിൻ്റെ വാല്യൂസ് ആണ് നമുക്ക് ഫൈനലി ഒരു ഫിൽറ്റർ ഡിസൈനിന് വേണ്ടത്. And that can be found by taking the inverse discrete Fourier transform of this sampled version of frequency response. Okay, so we'll see an example, and using this example we will also describe the steps in finding out the FIR filter using frequency sampling method. Okay, so the question is like this: design a linear phase FIR filter with omega c is equal to 0.5 pi radians per second by taking m is equal to 11. So as you already know, this m is the order of your filter. Order means how many non-zero elements of h of n will be there. That is called as the order. And omega c is the cutoff frequency. And since omega c is a digital frequency, the maximum value that it can have is pi, out of which it will cut off at 0.5 pi. Now, ht of omega is already given as, or the magnitude of ht of omega is given as 1 for frequencies from 0 up to 0.5 pi. Then there's a 0 from 0.5 pi to 1.5 pi. There's a 1 from 1.5 pi to 2 pi. ഇതാണ് നിങ്ങൾക്ക് തന്നിരിക്കുന്ന സ്പെസിഫിക്കേഷൻ. ഈ ഒരു ഫ്രീക്വൻസി റെസ്പോൺസ് കിട്ടാൻ വേണ്ടിയുള്ള ഒരു ഫിൽറ്ററാണ് നിങ്ങൾ ഡിസൈൻ ചെയ്യേണ്ടത്. So the first and foremost step in designing this filter is to list the specifications and draw the response. സ്പെസിഫിക്കേഷൻസ് ലിസ്റ്റ് ചെയ്യാന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ ഇപ്പോൾ ഈ ഒരു ക്വസ്റ്റിനകത്ത് the specification is the cutoff frequency is should be 0.5 pi. The value of m should be 11, and the frequency response should be like this. This is called as a specification. അപ്പം ആദ്യം ചെയ്യേണ്ട സ്റ്റെപ്പ് സ്പെസിഫിക്കേഷൻസ് ലിസ്റ്റ് ചെയ്യുക എന്നുള്ളതാണ്. ഫസ്റ്റ് വൺ, the response, the magnitude response is like this. You just write it down, that's all. Question ഉള്ള അതേപടി എടുത്ത് എഴുതും. ഇനി you want to draw the response, അതായത് with omega as x-axis and hd of omega or mod hd of omega as the y-axis, you draw the response. So when you draw, you see between omega equal to 0 to 0.5, the value is 1. And between 0.5 to 1.5, the value is 0. And between 1.5 to 2, the value is 1. So the frequency response will look like this in the omega axis. So this is the first step. In the second step, you choose an ideal response if it is not already given and sample hd of omega at m points by taking omega equal to omega k equal to 2 pi k by m, and the value of k varies from 0, 1, 2, 3 up to m minus 1 to generate the sequence capital H of k. So what you want to do is, you find out what is hd of omega, that is ideal response. ആ ഐഡിയൽ ഫ്രീക്വൻസി റെസ്പോണ്ടിനെ നമ്മൾ സാമ്പിൾ ചെയ്യും. സാമ്പിൾ ചെയ്യാന്ന് വെച്ചാൽ you are not going to consider all the frequencies. You are going to consider only the frequencies at k equal to 0, k equal to 1, k equal to etc. Okay. ഇനി എന്താണ് ഐഡിയൽ റെസ്പോൺസ് നമ്മൾ ഓൾറെഡി കണ്ടു കഴിഞ്ഞു. FIR ഫിൽറ്റർ ഡിസൈൻ ചെയ്യണമെങ്കിൽ the filter response frequency the phase response should be linear. So an ideal FIR filter will be like hd of omega is equal to some constant into e raised to minus j omega tau. ഇതാണ് നമ്മുടെ ideal FIR filter. And always we try to design the ideal FIR filter. So ideal FIR filter is something like c into e raised to minus j omega tau. So tau is a constant and the value is tau is given as m minus 1 by 2. This is also we have seen. Linear phase FIR filter ആണെങ്കിൽ ആ linear phase FIR filterന്റെ frequency response should be like this, where tau is a constant. Now what is C? For that you just go back to the magnitude response. In the magnitude response, whatever be the value given here, that is C, or it is a magnitude of hd of omega. In our case, the magnitude is 1 when the frequency range is between 0 and pi by 2 and 3 pi by 2 and 2 pi. Otherwise it is 0. So here we have considered the magnitude as 1. Why? Because in our specification the value is given as 1. So our hd of omega is e raised to minus j omega tau, where tau is m minus 1 by 2. Okay, and when you do m minus 1 by 2, you will get the tau value to be 5. So our hd of omega is e raised to minus j 5 omega. Now we are going to sample this, അതായത് omega equal to 2 pi k by m എന്നുള്ള രീതിയിൽ സാമ്പിൾ ചെയ്യാൻ പോകുന്നു. So wherever you see omega in this equation, you replace it by 2 pi k by m, which will give you where m is equal to 11. So you can write as 2 pi k by 11. So wherever in this equation you see omega, you replace it by 2 pi k by 11. So here you just replace it by 2 pi k by 11. So the omega here was 5 into omega. This is 5 into 2 pi k by 11. That is 10 pi k by 11. That is what is here. Okay. Now, so what we are going to do is, we know the range of k value is 0, 1, to up to m minus 1. The value of m is 11, so the range of k values is k equal to 0 up to 10. So when k equal to 0, what is the frequency? We already told that the value of omega is 2 pi k by m. So I can say as omega suffix k. So when k equal to 0, the value of omega 0 is 2 pi into 0 by 11, that is equal to 0. When k equal to 1, that is omega 1 will be 2 pi into 1 by 11, that is 2 pi by 11, that is 0.1818 pi. Similarly, when k equal to 2, it is omega 2 pi into k, which is 2 by 11, that is 0.363 pi. So k equal to 3, you substitute for 3, k equal to 4, you will get this value, omega 4, k equal to 5, you will get omega 5, and so on. So up to k equal to 10, you will get the values, because the value range of k is from 0 till 10. Okay. Now, so what we did here is actually the following. That is coming in step 3. So what we did here is actually the following. You have the frequency range 0 to 2 pi in omega. You have divided this into multiple uniformly separated frequencies. Okay, so this is at k equal to 0. At k equal to 1, the frequency is 0.18 pi. So that is this point. So the corresponding value is 1. This is our original HD of omega, which we have drawn like this. Okay. Previously, we were considering all the frequencies. Now we are not considering all the frequencies, we are sampling them. We are considering only discrete frequencies. കുറച്ച് ഫ്രീക്വൻസി മാത്രമേ നമ്മളിവിടെ കൺസിഡർ ചെയ്യുന്നുള്ളൂ. ഫോർ എക്സാമ്പിൾ കെ ഈക്വൽ ടു 0ൽ ഒമേഗ ഈക്വൽ ടു 0 ആണ്. കെ ഈക്വൽ ടു 1ൽ ഒമേഗ ഈസ് ഈക്വൽ ടു 0.1818 പൈ ആണ്. ദാറ്റ് ഈസ് ദിസ് ഫ്രീക്വൻസി വിച്ച് ഹാസ് എ വാല്യൂ 1. കെ ഈക്വൽ ടു 2ൽ ഇറ്റ് ഈസ് 0.363 പൈ ആണ്, which is this frequency whose value is 1. K equal to 3ൽ 0.5454 pi ആണ്, whose frequency is this and the value is 0. Similarly, K equal to 4ൽ the value of omega is 0.727 pi, whose value in our case is 0. And so on. So you can see that not for all values of k you will have a value for HD of omega. എന്ന് വെച്ച് കഴിഞ്ഞാൽ k equal to 0ലും k equal to 1ലും k equal to 2ലും മാത്രമേ നമുക്ക് values ഉള്ളൂ. That is equal to 1. K equal to 3, 4, 5, 6, 7 and 8, the values are 0. K equal to 9 and 10, the value is 1. So you can rewrite the equation of HD of omega after sampling as h of k, such that, and remember, h of k is hd of 2 pi k by m, that is e raised to j 5 into omega, that is 10 pi k by m minus. ഇതായിരുന്നു നമ്മുടെ h of k. ഈ h of kക്ക് kയുടെ വാല്യൂ 0യും 1ഉം 2ഉം ഉള്ളപ്പോൾ മാത്രമേ you have the magnitude equal to 1. Okay, otherwise it is 0. And for k equal to 9 and 10, so you can rewrite h of omega as h of k is equal to e raised to minus j 2 pi k by m into 5, that is e raised to minus j 10 pi k by 11 for k equal to 0, 1, 2, that is k equal to 0, k equal to 1, k equal to 2. ബാക്കിയുള്ള values 3, 4, 5, 6, 7, 8, the value of hd of omega is 0. And for 9 and 10, you have value e raised to minus j 10 pi k by 11. So now whatever you got is actually the DFT samples. You have sampled the frequency, continuous time frequency, to some discrete values, and you have found out which all values of k you have a magnitude value. That is what in step 3. In step 4, only thing you want to do is to compute the impulse response h of n. h of n കാണുക എന്നുള്ളതാണ്. ഇപ്പോൾ നമുക്ക് DFT സാമ്പിൾസ് h of k ആണ് കിട്ടിയത്, അതിൽ നിന്ന് h of n കാണുക എന്നുള്ളതാണ്. So you can do it in multiple ways. Either you can directly take the IDFT, okay, using the equation. IDFT equation വെച്ചിട്ട് you can easily find h of n, or you can use the following equation. ഈ ഇക്വേഷൻ വന്നത് എങ്ങനെയാണെന്ന് വെച്ച് കഴിഞ്ഞാൽ h of n എന്ന് പറയുന്നത് സിമെട്രിക് ആയിരിക്കും. വൺ ഓഫ് ദ ഇമ്പോർട്ടൻറ്റ് പ്രോപ്പർട്ടീസ് ഓഫ് ലീനിയർ ഫേസ് ഫിൽറ്റേഴ്സ് ഈസ് h of n is symmetric. h of n symmetric ആണെങ്കിൽ you can combine multiple values of h of n. Okay, for example, h of 0 യും h of m minus 1 ഉം സെയിം ആയിരിക്കും, h of 1 ഉം h of m minus 2 ഉം സെയിം ആയിരിക്കും. ഇൻ അവർ കേസ് h of 0 യും h of 10 ഉം സെയിം ആയിരിക്കും, h of 1 ഉം h of 9 ഉം സെയിം ആയിരിക്കും. അങ്ങനെയുള്ള കേസസ് കമ്പൈൻ ചെയ്തിട്ട് യു ക്യാൻ ഡിറൈവ് ദിസ് ഇക്വേഷൻ ഫോർ m is odd and for m is even. So you can directly substitute h of k നമ്മൾ we have already found out, that is this. You don't have any variable which is unknown, everything is known, so you can directly find out h of n. h of n is h of 0 plus sigma k equal to 0 to m minus 1 by 2. Okay, so this is this. M minus 1 by 2 is 5 into real part of h of k e raised to j 2 pi n k by 11. Okay, now h of 0 means you substitute k equal to 0 in h of k, you will get the value. h of k in general is e raised to minus j 2 pi k by m into 5 e raised to minus j 10 pi k by n multiplied by your Twiddle factor. So if you just combine these two, you'll get this. Okay, and you need to note here is that, see here, the summation is only till 2. The reason is being, if you look at h of k, you see that from k equal to 0 to 1, 0 to 2, you have the value equal to e raised to minus j 10 pi k by 11. After that, 3, 4, 5, the value is 0. So you don't want to consider those for addition. Okay, so k is ranging from 0 to 2 instead of 0 to 5. Okay, and then RE means it is the real part of e raised to j 2 pi k by 11 into 5 minus n. Now e raised to j theta is cos theta plus j sin theta, and the real part is cos theta. So the real part of e raised to j 2 pi k by 11 into 5 minus n is cos of 2 pi k by 11 5 minus n. h of n കാണണമെങ്കിൽ നമുക്ക് n ന്റെ value should be from 0, 1, 2 up to m minus 1, which is 10. So you substitute for n equal to 0 and you need to find each and every coefficient. Okay, before that you need to find out, so there is a summation here, k is varying from 0 to 2. So you put k equal to 0, it is here, it will be cos 0, which is equal to 1, k equal to 1, which is cos 2 pi 11 into 5 minus n, and k equal to 2, which is cos 4 pi 11 by 11 into 5 minus n. So your h of n equation can be expanded as 1 by m, which is 1 by 11, into h of 0 is 1 plus 2 into cos of 2 pi by 11 5 minus n plus 2 into cos of 5 pi by 11 5 minus n. ഇത്രയും കിട്ടുമ്പോൾ എച്ച് ഓഫ് എന്നിൻ്റെ ജനറൽ ഇക്വേഷൻ, ദിസ് ഈസ് ദ ജനറൽ ഇക്വേഷൻ ഓഫ് എച്ച് ഓഫ് എൻ ഇൻ ദിസ് പ്രോബ്ലം. നമുക്ക് എച്ച് ഓഫ് എൻ മാത്രം കിട്ടിയാൽ പോരാ, എന്നിൻ്റെ ഓരോ വാല്യൂസിനും എച്ച് ഓഫ് എന്നിൻ്റെ വാല്യൂ എന്താണെന്ന് കിട്ടണം. സോ വാട്ട് യു വാണ്ട് ടു ഡു ഈസ് യു സബ്സ്റ്റിറ്റ്യൂട്ട് n equal to 0 and you find out what this value is. That means for finding h of 0, you substitute n equal to 0. എവിടെയൊക്കെ n കാണുന്നുണ്ടോ അവിടെയെല്ലാം 0 സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്യും. അങ്ങനെ സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്ത് ചെയ്യുമ്പോൾ you will get 1 plus 2 cos 2 pi by 11 into 5 plus 2 cos 4 pi by 11 into 5. And that you will get as 0.0694. Similarly, to find h of 1, you substitute n equal to 1. ഇവിടെ n-ന്റെ വാല്യൂ 1 കൊടുക്കുക. You will get the corresponding value of h of 1, which is minus 0.054. Similarly, you can give for 2, h of 3, h of 4 and h of 5, you will get these values. ഇനി നമുക്ക് 10 വരെ വാല്യൂസ് കണ്ടുപിടിക്കണം, h of 10 വരെ കണ്ടുപിടിക്കണം. പക്ഷേ h of n is symmetric. As I said earlier, h of n is equal to h of m minus 1 minus n, where m is equal to 11, which means that h of 0 will be h of 10, h of 1 will be h of 9, and it goes like h of 4 will be h of 6. So you can write by, or you just need to find out only half of the values. The rest of the value will be symmetric. Okay. So we have actually done the most important part in the impulse response in the design of the filter, that is to find the coefficients of impulse response. ഇതാണ് ഈ ഒരു ഏതെങ്കിലും ഒരു FIR ഡിസൈൻ പ്രോബ്ലത്തിലെ ഏറ്റവും ഇമ്പോർട്ടൻ്റ് ആയിട്ടുള്ള കാര്യം എന്ന് പറഞ്ഞാൽ ഇമ്പൾസ് റെസ്പോൺസ് സ്മോൾ h of n-ന്റെ വാല്യൂസ് അറ്റ് n equal to 0, 1 up to m minus 1 അത് കണ്ടുപിടിക്കുക എന്നുള്ളതാണ്. അത് നമ്മൾ കണ്ടുപിടിച്ചു. ഇനിയുള്ളത് ജസ്റ്റ് ആൻ എക്സ്ട്രാ സ്റ്റെപ്പ് വേർ you will find out the set transform of h of n. So set transform എടുക്കണമെങ്കിൽ n equal to 0 to m minus 1 ആണ്, m-ന്റെ വാല്യൂ 11 ആണ്, so it is m equal to m minus 1 is 10, so n equal to 0 to 10, h of n set raised to minus n. So h of n for each value of n you know, 0, 1, 2 up to 10 you know. So you just substitute it and you can simplify this like this, because h of 0 ഉം h of 10 ഉം same ആണ്. You can combine them. This is that combination. h of 1 ഉം h of 9 ഉം same ആണ്, and you can combine them and you get this combination and so on. So this is how you can design an FIR filter. Designing an FIR filter means finding out the coefficients of impulse response. Small h of n-ന്റെ അല്ലെങ്കിൽ you call the coefficient of impulse response, അതിൻ്റെ വാല്യൂസ് കണ്ടുപിടിക്കുക എന്ന് പറയുന്നതാണ് FIR filter design എന്ന് പറയുന്നത്. ആ FIR filter design you have done using frequency sampling method. Again, frequency sampling method means you get the actual filter HD of omega, you sample at 2 pi k by m, where m is the number of points or number of order of the filter. You find, basically when you sample it, you are actually doing a DFT. You just take the inverse DFT, find the impulse response h of n, you find for each value of n what is the corresponding values of h of 0, h of 1, h of 2, etc. That will finish your design. അപ്പോൾ ഇത്രയും പറഞ്ഞതിൽ എന്തെങ്കിലും ഡൗട്ട് ഉണ്ടെങ്കിൽ ചോദിക്കാം. Okay, so we'll go to the next one, which is the IAR filter design. Okay. IR filter design, actually there are FIR filter design, there are multiple ways of designing the filter, out of which two of them are very easy. That is inverse invariance method and bilinear transformation. There is one more filter called as Butterworth that needs some time. Okay, so in our session today, we will see the first two, the inverse invariance method and bilinear transformation, and we will see the Butterworth filter design in the next class. Okay, so basically the digital filters are of two types, FIR and IIR. IIR means infinite impulse response. So in an IIR filter, the current output y of n is a function of past output, present and past input. That means if you write the difference equation of IIR filter, you can write y of n as sum a1 y of n minus 1 plus a2 y of n minus 2, which means it is depending on the past output, plus x of n plus sum b1 x of n minus 1 plus, and it goes, which is the past input, present and the past input. Okay, so that is an IR filter. IR filter design is a bit different from FIR filter design. FIR filter design we know there is a linear phase filter. A linear phase filter just inverse Fourier transform or inverse DFT, you'll get the inverse response. If you want, you can multiply it with windows so that it is truncated. IR filter design, it is a bit different. Difference is like this. To design a digital IR filter, the specifications of an analog filter will be provided. Digital IR filter design ചെയ്യാൻ വേണ്ടി നമുക്ക് തരുന്നത് ഒരു അനലോഗ് ഫിൽറ്ററിൻ്റെ സ്പെസിഫിക്കേഷൻസ് ആണ്. അനലോഗ് ഫിൽറ്റർ എന്ന് പറഞ്ഞാൽ it might be like the frequency response, like the Laplace transform of transfer function. അല്ലെങ്കിൽ ട്രാൻസ്ഫർ ഫംഗ്ഷൻ തന്നെയായിരിക്കും നിങ്ങൾക്ക് തരുന്നത്. ഇമ്പൾസ് റെസ്പോൺസിൻ്റെ കണ്ടിന്യൂസ് ടൈം ഡൊമൈനിലുള്ള ഇമ്പൾസ് റെസ്പോൺസിൻ്റെ ഒരു ലാപ്ലാസ് ട്രാൻസ്ഫോം വേർഷൻ ആയിരിക്കും നമുക്ക് തരുന്നത്. That is the actual specification of an analog filter. അതിൽ നിന്ന് from the analog design, using variable substitution, a digital filter is designed. ആ ഒരു അനലോഗ് ഫിൽറ്ററിനെ നമ്മൾ you convert it to a digital filter by substituting instead of S means the Laplace transform, the S domain S. Instead of S, you substitute a conversion in which you can convert the analog frequency to digital frequency. Our substitute chamber, you will get the corresponding digital filter. So the analog filter is actually specified using the transfer function that is in Laplace domain, that is HA of S, where A represents the analog, is the ratio of B of S by A of S, in which B of S will be a weighted sum of powers of S divided by weighted sum of powers of S in the denominator. This is the transfer function of an analog filter. Okay, and this you are going to convert it to digital filter by doing some substitution for S. S in ചില substitutions ആ ഒരു ഇക്വേഷൻസിൽ വരുത്തി കഴിഞ്ഞു കഴിഞ്ഞാൽ you can convert it to a digital filter. പക്ഷെ അങ്ങനെ സബ്സ്റ്റിറ്റ്യൂഷൻ ചെയ്യണമെങ്കിൽ അനലോഗ് ടു ഡിജിറ്റൽ കൺവേർഷൻ ഈസ് എഫക്റ്റീവ്. അങ്ങനെ എഫക്റ്റീവായിട്ട് സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്യണം. അനലോഗ് ഫിൽറ്ററിൻ്റെ പ്രോപ്പർട്ടീസ് മാറാതെ ഡിജിറ്റലിലേക്ക് കൺവേർട്ട് ചെയ്യണം. പ്രോപ്പർട്ടീസ് എന്ന് വെച്ചാൽ സ്റ്റെബിലിറ്റി, കോസാലിറ്റി അങ്ങനത്തെയുള്ള പ്രോപ്പർട്ടീസ് ഒന്നും മാറാതെ ഡിജിറ്റലിലേക്ക് കൺവേർട്ട് ചെയ്യണം എന്നുണ്ടെങ്കിൽ we should make sure these 2 points are taken care of. What are the points? J omega axis in S plane is mapped on the unit circle in Z plane. So you are converting from analog to digital. ഇതാണ് ചെയ്യുന്നത്. Analog domain you have the S plane. Digital domain you have the Z plane. Okay. So that means in analog domain, whatever is there in the j omega axis, analog means S is equal to sigma plus j omega. Again, be careful here. Capital omega is the analog frequency and small omega is the digital frequency. Okay, don't interchange them. Interchange കഴിഞ്ഞാൽ everything will be wrong. So capital omega എന്ന് പറയുന്ന notation, it is the analog frequency. Small omega, W ന്റെ രീതിയിൽ എഴുതുന്ന notation, that is a digital frequency. Don't interchange or don't confuse them. Okay. So in analog domain, j omega axis should be mapped to the unit circle. Okay. So also the left hand side of the S plane should be mapped to inside of unit circle. A filter is stable if it has poles only in the left hand side. S ഡൊമൈൻ്റെ അല്ലെങ്കിൽ എസ് പ്ലെയിൻ്റെ LHSൽ മാത്രം ആണ് ജെ ഒമേഗ ആക്സിസിൻ്റെ ലെഫ്റ്റ് സൈഡിൽ മാത്രമാണ് പോൾസ് എങ്കിൽ ആ ഒരു അനലോഗ് ഫിൽട്ടർ സ്റ്റേബിൾ ആയിരിക്കും. അപ്പോൾ നമ്മൾ ഡിജിറ്റലിലേക്ക് കൺവേർട്ട് ചെയ്യുമ്പം ആ സ്റ്റെബിലിറ്റിക്ക് മാറ്റം വരാൻ പാടില്ല. എന്ന് വെച്ച് കഴിഞ്ഞാൽ എന്ത് വെച്ചാണോ നമ്മൾ കൺവേർട്ട് ചെയ്യുന്നത്, ഇറ്റ് ഷുഡ് മേക്ക് ഷുവർ ദാറ്റ് എസ് ഡൊമൈനിലെ ലെഫ്റ്റ് ഹാൻഡ് സൈഡിലെ പോൾസ് ഷുഡ് ബി മാപ്പ് ഇൻസൈഡ് ദ യൂണിറ്റ് സർക്കിൾ. യൂണിറ്റ് സർക്കിളിനകത്ത് ഡിജിറ്റൽ ഫിൽറ്ററിന് പോൾസ് വന്നാൽ അത് സ്റ്റേബിൾ ആവത്തുള്ളൂ. ഓക്കെ, ഇങ്ങനൊരു സിറ്റുവേഷൻ ഇഫ് യു ക്യാൻ മേക്ക് ഷുവർ of whatever conversion we are using, then that digital filter is causal and stable. So these 2 points should be taken care of. So the first method of IR filter design is called as impulse invariant method. Okay, what it means is unit impulse response h of n is the sampled version of impulse response of analog filter. അനലോഗ് ഫിൽറ്ററിന് ഒരു ഇമ്പൾസ് റെസ്പോൺസ് ഉണ്ടാവും. ഫോർ എക്സാമ്പിൾ എച്ച് ഓഫ് ടി അനലോഗ് ആയത് കാരണം കണ്ടിന്യൂസ് ടൈം ആയിരിക്കും. ഇതിൻ്റെ സാമ്പിൾഡ് വേർഷൻ മീൻസ് യു ആർ സാമ്പിളിങ് ഇറ്റ് അറ്റ് എൻ ടി. ടി എന്ന് പറയുന്നതാണ് സാമ്പിളിംഗ് പീരീഡ്. ആ സാമ്പിളിംഗ് പീരീഡിനെ സാമ്പിൾ ചെയ്യുന്നതിനെയാണ് യു വിൽ കോൾ ഇറ്റ് ആസ് യൂണിറ്റ് ഇമ്പൾസ് റെസ്പോൺസ് ഓഫ് എച്ച് ഓഫ് എൻ. ഓക്കെ, നൗ so your h of z is sigma n equal to 0 to infinity h of n z raised to minus n. This is the general equation of z transform. You substitute z is equal to e raised to st, where t is the sampling period. E equation substitute here. So you can say h of z is equal to sigma n equal to 0 to infinity h of n. N z we know that it is e raised to st. So e raised to minus stn by. Now S is actually for analog domain. So the Laplace transform can be written as sigma plus j capital omega, where capital omega is the analog frequency. And Z is actually r e raised to j omega, which represents the circle with radius is equal to r and system of circles. Okay, so z is equal to r e raised to j omega. Now when you substitute these two to this equation, z is equal to e raised to st, then you can write the left hand side z is r e raised to j omega. In the right hand side it is e raised to st, where s is sigma plus j omega. So e raised to sigma plus j omega into t. Okay, Now you can split e raised to sigma plus j omega into t as one real term, that is e raised to sigma t, and one imaginary term, which is e raised to j omega t. And you equate in left hand side and right hand side the real and imaginary terms. So you can see that r is e raised to sigma t and omega is equal to capital omega t. Okay, so where r is the radius and sigma, capital sigma, is represents the real axis in the s domain. So if you look at this equation, when sigma equal to 0, r is equal to 1. That means sigma equal to 0 means it represents the j omega axis. R equal to 1 means it represents the unit circle. So we have mapped j omega axis to unit circle. In a similar way, when sigma is negative, r is less than 1. We put sigma some negative value here. Then the value of r is less than 1. Or ineffective, I have mapped the left half of S plane to inside of unit circle. Okay, so we have satisfied the conditions that we have mentioned earlier by doing this substitution, and this is called as impulse invariant method. And the thing you should note here is the relation between digital frequency and analog frequency. So digital frequency is equal to the analog frequency multiplied by the sampling period. This is the conversion in impulse invariance method. Okay. Now, how will I now use this knowledge to design the filter? So let HA of S is the transfer function of analog filter. Okay. Which can be, any transfer function can be expressed in partial fractions. You can express it as sum of ratios of terms. That is, h of s is some c1 by s minus p1 plus c2 by s minus p2 plus up to cm by s minus pm, where p1, p2 and up to pm are called as the poles. Or in general, you can express it as summation k equal to 1 to m ck by s minus pk. If you take the inverse of this Laplace transform, you will get the continuous time impulse response HA of t for the analog filter as sigma k equal to 1 to m ck e raised to pkt. Okay, now e raised to pkt you get because 1 by s minus pk has its inverse Laplace transform e raised to pkt. That's how you get here. Now this is continuous. What I want is digital. So I sample this at t equal to nt, where t is the sampling period or sampling interval. So wherever I see t, I'll replace it by nt, which means I have a sequence for each value of n. So HA of n is sigma k equal to 1 to m ck e raised to pk. Instead of t, it is n into t. Now when you take the set transform, h of z is equal to, so we are going to take the set transform of this sigma n equal to 0 to infinity h a of n, which is this, into z raised to minus n. When you take this set transform, the value that you get is this sigma k equal to 1 to m ck 1 minus e raised to pkt z raised to minus 1, which means you are mapping 1 by sigma, or in other words, you have mapped ck by s minus pk to 1 by 1 minus e raised to pkt z raised to minus 1. You have converted the analog transfer function to a digital transfer function, and this is the mapping. Okay, if the sampling rate is high, that is when t value is less than 1, then you need to multiply by t also. That's only change you want to do. Okay, so basically the relation between analog and digital frequency that we have already mentioned is the analog frequency capital omega is digital frequency by t, or digital frequency is equal to capital omega multiplied by t. So the mapping or the transformation is as follows. If the impulse response is in the form, or sorry, if the Laplace transfer function is of the form a by s minus p, then the corresponding digital domain substitution is 1 by 1 minus e raised to pt z raised to minus 1. Similarly, if the Laplace transform or the transfer function is of this form, you just substitute it with this expression. Similarly, if the Laplace transform is of this form, you substitute it with this expression. That's all. Okay. To show you how this is done, let us do a problem. So in this problem, you are given an analog transfer function. For an analog transfer function of h of s is equal to 2 by s square plus 3s plus 2. This is the analog transfer function. Determine h of z. You want to find the z transform of the digital filter using impulse invariant transformation for sampling period 1 second and sampling period 0.1 second. Okay, so the first step in doing this is to write down the specification. Okay, so if the transfer function is not given, then you need to derive the transfer function in the analog domain. For example, the question might be like, in analog domain, the filter has poles at s is equal to minus 1, s equal to minus 2. Then you need to find out what is a transfer function. Okay, so in our case, in this problem, the transfer function is already given. So h of s is 2 by s square plus 3s plus 2. In step 2, you need to select the sampling rate. Now, sampling rate is already given in this question. T equal to 1 second, A part, T equal to 0.1 second, B part. So you just need to select the sampling rate if it is not already given. Step 3, express transfer function as a sum of poles by using partial fractions. H of s is 2 by s square plus 3s plus 2 എന്നുള്ളതാണ് ട്രാൻസ്ഫർ ഫംഗ്ഷൻ. അതിനെ പാർഷ്യൽ ഫ്രാക്ഷൻ ആക്കുക എന്ന് വെച്ചാൽ ഇറ്റ് ഷുഡ് ബി എക്സ്പ്രസ്ഡ് ആസ് a by s plus 1 plus b by s plus 2. ഓക്കെ, നിങ്ങൾക്ക് ഇത് ഓൾറെഡി അറിയാം എന്ന് എനിക്ക് തോന്നുന്നു. സോ ഐ എം നോട്ട് ഗോയിങ് ഇൻ ഡീറ്റെയിൽസ് ഓഫ് ദിസ്. സോ ടു ഫൈൻഡ് a, you set s equal to minus 1 for all the terms in the left hand side except s 1 by s plus 1. അങ്ങനെ കൊടുത്തു കഴിഞ്ഞാൽ and you substitute s equal to minus 1, you will get the value of a as 2. To find b, you substitute all the values on the left hand side having s with minus 2 except for s plus 2, 1 by s plus 2. That is substituted you will get b. So your h of s will be like 2 by s plus 1 minus 2 by s plus 2. This is your h of s. Okay, so that is your step 3. So you have found out the partial fraction of your transfer function. Step 4 is to compute the set transform of digital filter using the transformation. So transformation is, if your transfer function term is something like this, ai by s minus pi, the corresponding transformation is ai by 1 minus e raised to pit z raised to minus 1. Okay, So 2 by s plus 1 will become 2 by 1 minus e raised to minus t z raised to minus 1, and minus 2 by s plus 2 will become minus 2 divided by 1 minus e raised to minus 2 z raised to minus 1. You just apply this, that's all. Now, the value of t is already given, t equal to 1, means you substitute for t equal to 1 here, you get the expression. For t equal to 0.1 seconds, you substitute for t equal to 0.1, you'll get the expression. But for t equal to 0.1, the value of t is less than 1, which means you need to multiply or normalize the transfer function. You can normalize the transfer function by multiplying it with t. So the new normalized transfer function hn of z is equal to t multiplied by h of z. So you have the normalized transfer function. This is how you design an IR filter using impulse invariant method. Okay, so just look at this problem. If you go step by step, ella filter design there are number of steps. If you know the steps, the filter design is very easy. If you miss any step, it will create error in your solution. Okay, I hope you have understood impulse invariant method. Any questions? Okay, fine. The next method is called as bilinear transformation. Okay, again idum same രീതിയിലാണ് s-നും z-നും തമ്മിൽ there is a relation, just need to substitute the relation, that's all. Okay, so in bilinear transformation also it provides a relationship between s and z domain. All points in the left hand side of s domain are mapped inside the unit circle of z domain, and all points in the right hand side of the z domain are mapped outside of unit circle of z domain. Okay, and what you want to substitute for h of s is you substitute s is equal to 2 by t 1 minus z raised to minus 1 by 1 plus z raised to minus 1. ഇതാണ് സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്യുന്നത്. അപ്പോൾ നിങ്ങളുടെ ക്വസ്റ്റ്യനകത്ത് എച്ച് ഓഫ് എസ് എന്ന് പറയുന്ന ഒരു ട്രാൻസ്ഫർ ഫംഗ്ഷൻ വിൽ ബി ഗിവൻ. ആ എച്ച് ഓഫ് എസിലെ എസിന് പകരം യു സബ്സ്റ്റിറ്റ്യൂട്ട് ഇറ്റ് ആസ് 2 by t 1 minus z raised to minus 1 by 1 plus z raised to minus 1. അത്രേ ഉള്ളൂ. ഇനി അതിൽ ചെറിയൊരു അനാലിസിസ് ഉണ്ട്. Let z can be represented as r into e raised to j omega. Okay, now so s is sigma plus j omega. So sigma plus j omega is equal to, you substitute z equal to r e raised to j omega. So this will become 2 by t 1 minus, say r inverse here, 1 minus r inverse or r e raised to j omega whole inverse by 1 plus r e raised to j omega whole inverse. So which will become this. Now we know that e raised to j theta is cos theta plus j sin theta. So e raised to j omega is cos omega plus j sin omega. So sigma plus j omega will become 2 by t. You can expand this r e raised to j omega, multiply denominator and numerator by the conjugate of the denominator. That will give you this equation. And this equation has real part and imaginary part. So you equate real to real and imaginary to imaginary on both LHS and RHS. So sigma will be equated to here, and omega, capital omega, will be equated to the imaginary part. So I can write sigma is equal to 2 by t r square minus 1, 1 plus r square plus 2r cos omega. Now if you see in this equation, if you put r equal to 1, which is the unit circle, then the value of sigma will become 0. R equal to 1 means 1 minus 1, this is 0. So that means it has mapped the the j omega axis to the unit circle. Unit circle is already mapped. If you put r is less than 1, then the value of sigma will be less than 0. Okay, you can try this by substitution here. ഇവിടെ r value, let's say 0.5 കൊടുത്തു കഴിഞ്ഞാൽ 0.5 minus 1 is minus 0.5. R square is positive. R is always positive, so 2r is positive, so sigma will become negative. Or you have mapped the left hand side of the S plane to inside the unit circle. So you have done the whatever conditions should be done while mapping. They have made it proper. Next is, then what is the relation between analog frequency and digital frequency? To find the relation, you put r equal to 1, which is basically you are evaluating on the unit circle, or you are just looking at the frequency response. When you put r equal to 1, the relation that you get is the analog frequency capital omega is equal to 2 by the sampling period into tan of the digital frequency by 2. ഇതാണ് conversion. Okay? This is the relation between analog frequency and digital frequency while doing the bilinear transformation. This is given in the next statement. Okay, so you see the analog frequency is 2 by t tan of digital frequency by 2. Or you can write the digital frequency is 2 into tan inverse of analog frequency into sampling period by 2. Okay, that's all. Now, the exercises are simple. For example, the same question as that of previous. You want to find the digital transfer function using bilinear transformation corresponding to the analog transfer function h of s is 2 by s square plus 3s plus 2 for t equal to 1 second. Now there is only one step. Wherever you see s in the analog transfer function, you substitute it with s equal to 2 by t 1 minus z raised to minus 1 by 1 plus z raised to minus 1. അപ്പം h of s നിങ്ങൾക്ക് തന്നിട്ടുണ്ട്. ബൈലീനിയർ ട്രാൻസ്ഫോർമേഷൻ വെച്ചിട്ട് ഇതിൻ്റെ കറസ്പോണ്ടിങ് ഡിജിറ്റൽ ഫിൽറ്റർ കാണണം എന്നുണ്ടെങ്കിൽ എസിന് പകരം you just substitute it with 2 by t 1 minus z raised to minus 1 by 1 plus z raised to minus 1. So that's what we have did here. S equal to 2 by t 1 minus z raised to minus 1 by 1 plus z raised to minus 1. ചെയ്യുമ്പോൾ this is s square, this is s. Okay, you just substitute it. But അവിടെ വെച്ച് നിർത്തരുത്. Make sure you simplify this so that you will have powers of z raised to minus 1 in the numerator and in the denominator. ഇതൊരു വല്ലാത്ത രീതിയിലാണ് ഇപ്പം ഇതിനകത്ത് ഈ ഒരു expression കിടക്കുന്നത്. You simplify this so that you will have it in proper power value. Okay, so what I did was I just took out square. So this is 4 by t square, 1 minus z raised to minus 1 by 1 plus z raised to minus 1, that square. 6 by t 1 minus z raised to minus 1 by 1 plus z raised to minus 1 plus 2. Now you multiply and divide the denominator by t square 1 plus z raised to minus 1 whole square. So it will become like this. Then you bring t square 1 plus z raised to minus 1 whole square to the numerator. So it comes like this. So this is a good expression. Now you substitute t equal to 1. So wherever you see t, you substitute it as 1. That's our question. So 2 into 1 plus 2 z raised to minus 1 plus z raised to minus 2. Okay, and you will have the denominator. Now you can still simplify this. 4z, so all the terms of z raised to minus 2 will get cancelled out because there is 4 z raised to minus 2 minus 6 z raised to minus 2, 2 z raised to minus 2, which is 0. If you add everything, it is 0. You can add the constants and the rest of the term comes like this. Up to, you need to do up at least up to here. You can still simplify further. You can take 12 out in the denominator and you can divide 2 by 12, 4 by 12 and 2 by 12. So we'll get the final expression as this. അപ്പം ബൈനറി ട്രാൻസ്ഫോർമേഷനിൽ make sure that you know how to simplify the things. That is very important. That you can do it only if you try out as much problems as possible. Okay, so this is bilinear transformation. Bilinear transformation, h of s എന്ന് പറയുന്ന ട്രാൻസ്ഫർ ഫംഗ്ഷൻ തന്നിട്ടുണ്ടെങ്കിൽ just substitute the value as s equal to 2 by 3 1 minus n raised to minus 1 by 1 plus n raised to minus 1. അത് വെറുതെ സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്യുക, സിംപ്ലിഫൈ ചെയ്യുക, അത്രേ ഉള്ളൂ. ദാറ്റ് ഈസ് യുവർ IAR filter. Okay, that's all from bilinear transformation. Anybody have any doubts regarding bilinear transformation? Okay, so doubts on the then I think we'll stop it here. We have one more method of IAR filter design, which is the Butterworth method. It takes some time to explain that, so we will do it maybe tomorrow. I think we have special class maybe during that time, or if you haven't finished by that time, then we will do it when we